let me give a new example, which has got junctions and elevations. So you have, let's say, some reservoir from which a pipe is coming. Let's call this reservoir 1. This another one. Okay. Then there is another one. Okay, so this reservoir 1, this is reservoir 2, that's reservoir 3. And all of them are filled with some fluid. Okay, let's say this is at an elevation is Z1, this is at an elevation is Z2, and this is at an elevation is Z3. Now, what is going to happen is that the fluid from the highest reservoir or the highest two reservoir is going to flow into the third reservoir. You do not know what it is, and let's say your interest is to calculate what is the flow rate through each of these pipes. Okay, so let's assume that Q1, Q2, Q3 are the flow rates, but you do not know what is Q1, Q2, Q3. You do not know what is the pressure drop, except that you just know that it's all at different elevations. So here we will have P atmospheric, here we will have P atmospheric, here we will have P atmospheric. So the flow rate Q1 is determined by the atmospheric pressure, okay, and then this hydrostatic head. So it's really Z1 that determines what is the flow rate through Q1, and that would generate a pressure difference between the top of the reservoir and this point at the junction. Similarly, there will be a pressure drop across your second pipe, there will be a pressure drop across your third pipe. So you can write down general equations. You can say that your H1, which is the pressure drop across the first pipe, is given by delta P1 by rho g, that's the pressure drop, plus delta Z1. So that is essentially, so that's the definition of our head loss. Okay, so far we have not been taking Z into consideration because we never worried about elevation changes, and that's equal to F into L1 by D1 into V1 square by 2G. Okay, where V1 we do not know, but we know it in terms of Q1, so let's write it as F1 into L1 by D1 into Q1 by A1 whole square, and then there's a 1 by 2G. Okay, similarly H2 is equal to delta P2 by rho G plus delta Z2, that's equal to F2 into L2 by D2 into V2 square by 2G, or that's equal to F2 into L2 by D2 into Q2 by A2 whole square into 1 by 2G. Similarly, H3 equal to delta P3 by rho G plus delta Z3 equal to F3 into L3 by D3 into V3 square by 2G, that's F3 into L3 by D3 into Q3 by A3 whole square into 1 by 2G. Okay, now what we know is that H1, H2, H3 should be different because Z1, Z2, Z3 are different, but delta P1, delta P2, delta P3 should be same because on one side it's all exposed to atmosphere, and delta P1 is what? The pressure difference between the top of this reservoir and this junction. Similarly, delta P2 will be the pressure difference between the top of the reservoir and this junction in which three pipes join, and then so is delta P3. So we would know delta P1 is equal to delta P2 is equal to delta P3. So that's one thing that we know, and therefore what you can do is you can start again. You need an iterative procedure. Let's say assume delta P. So let's call it equal to delta P. Assume delta P. So if you know delta P, then what you can do is that let's take the first equation, which is that. So let's write it down. If you assume delta P, then delta P by rho G plus delta Z1 is equal to F1 into L1 by D1 into Q1 by A1 whole square into 1 by 2G. So you assume F1, calculate Q1, check Reynolds number, check RE gives assumed F1, that's this F1. If not, continue till you get a F1 Q1 consistency. Okay, so then you can do that and repeat the same for Q2 and Q3, and once you get Q1, Q2, Q3, then you know that Q1 plus Q2 plus Q3 should be equal to 0. If not, then you have to go and change your assumed delta P and the process to be continued. So what am I trying to say? I'm trying to say that you can, for example, assume delta P. You know the equation for each pipe, so you can solve for what is velocity in each pipe. But when you try to do that, you would not know what is the friction factor. So you have to assume a value of friction factor, find out the velocity in each pipe, okay, and you have to do that in an iterative manner so that you get an F1 V1 or an F1 Q1 combination that satisfies the assumed delta P. And then you can do the same thing for second pipe, you can do the same thing for third pipe. That means you have gotten the flow rate for first, second and third pipe. But you also know that you are actually looking at a junction and there can't be a net flow. So Q1 plus Q2 plus Q3 should be equal to 0. So you can check that condition, and if that condition is violated, that means this delta P that you have assumed, the one which you started with, is actually the wrong one, and you need to change that as value and then continue this procedure till you find that Q1 plus Q2 plus Q3 equal to 0. So this is, for example, one way of solving this set of equations. As I mentioned earlier, you can come up with any procedure so that this condition is satisfied. So the point to note is that as far as the junction is concerned, there is no net flow through that, okay, or whatever is coming into that junction, the flow, it should be such that that fluid flow should go out, okay, or incoming flow should be equal to outgoing flow. As long as you impose that condition and your solution satisfies that, that's going to be your solution. So in general, whenever you have a system, it's you, let's say you have a pipe, it might be a complicated one. Let's say something like this, okay. So there is a fluid that's going to go like that. There's a bifurcation and then it goes that way, it goes this way, and so on, okay. A complicated system. What you can do is that, given this, that if I take any loop, let's say a loop that you start from there and finish that loop, and if I'm coming back at that point, then you can insist that there cannot be a pressure drop across a closed loop because I'm starting from the same point and ending at the same point. So you can insist that there cannot be a net pressure drop across a closed loop. Second thing that you can say is that there cannot be a net flow through any junction. So these are the two constraints that you should impose, and if you are trying to impose that constraint, and then you are going to get all values for velocity, you are going to get Reynolds number for each pipe, and then you can insist that all um, friction, all velocities that you calculate or flow rates that you calculate should satisfy friction factor correlations, Moody's chart. Okay. So as long as you write down set of relations that satisfy these three constraints, then you basically will have a system that needs to be solved. Okay, and most of the times you would end up the solution being in an iterative form because you will have more than one unknowns, and the equations may not be straightforward to do it. And remember, when I have done all these calculations, I have assumed all minor losses to be 0, but the minor losses should be accounted for because we know that it can play a major role. So then it will really depend upon the system that you are looking at. So so for example, when you write down the total head loss, you should write down the total head loss due to the length of the pipe as well as that due to the minor losses like bends and valves and so on in the system. So it becomes a very system specific configuration. But what we have done is really look at what are the constraints that you should impose. Okay, so the constraints would be, one is coming from the mass conservation, which is about how a flow gets divided or added up. The second is about coming from the force balance, which is about your pressure loss, okay, or how does the pressure drop, whether they get added or equally divided and so on. So these are the two rules that you should remember. I just realized that while I wrote the first problem, I have not taken a 1 by 2g into consideration. So here when I replace V1 with Q1 by A1, there is a factor of 1 by 2g. There is a factor of 1 by 2g. There is a factor of 1 by 2g, which would appear in expressions for Q1, Q2 and in Q3, and when you have substituted, that would again come. So that's 1 by 2g, 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 and 1 by 2g. Okay, it's just coming as a factor. Okay.